The last example is a vehicle routing problem. Vehicle routing problems are a type of traveling salesperson problem, whereby you have a salesperson that must deliver or stop or visit a number of locations in a given time period. And you need to find the optimal order of the stops that that salesperson would make, such that they minimize, let's say, the total time traveling to maximize other things such as delivery pickup or sales pitches. So vehicle routing problems are generally used in all kinds of industries. Amazon uses them. Your pizza delivery company may or may not use them depending on the size of it and whether it has a GIS division. And of course, delivery companies all over. There's all kinds of express delivery companies, UPS, and a whole bunch of them. And they have a number of drivers or agents and their vehicles, and the vehicles have to visit a certain number of stops in an optimal way. And that's done using vehicle routing problems. And there are a number of aspects to this that we're not even going to talk about at all, just because they can be more complex. But we're going to look at just the basics, enough to give you some confidence to apply the technique if you had to use it, and to figure out how you could use it in a particular situation with some confidence as well. Just as an extra, vehicle routing problems are also possible. They're just not possible in our version of ArcGIS Pro. They're only possible in the latest version of ArcGIS Pro and in ArcGIS Desktop, the place where we created the network data set. So ArcGIS Pro 2.6 contains the ability to do vehicle routing problems. And this is part of fleet management and optimization. This is the type of stuff that delivery companies do all the time, and they utilize this approach. We have a whole bunch of locations that have to be serviced. And then we have agents that service those locations. And the agents that service the locations could be one or could be many. So you could have one, let's say, delivery person or many delivery people that need to service all these locations. And then for each person, we need to find the best route. So it could be that way, for example. The optimal route or the optimal order of routes. So the optimal order of routes. And how do we do that? Well, we can try out different things. Let's say we have one driver, and the driver starts here at the green cross, and then has to deliver to each of these locations as an example. That's called a traveling salesman problem. So how do we find the most efficient way? Well, there's a brute force method, right? So we could figure out, okay, this is the order of stops that you should make based on this network and its impedances of time. So it could be, okay, go here, 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 and here, and then over to here and here. That's one possible route, right? Another possible route could be go to here first. Here, 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 and here. That's another possible route, and we could figure out, okay, what's the time for that? We'll call that time 1. What if we first go to this one, and then to this one, to this one, to this one, this one, this one, this one, this one, and this one, and that one? That would be time 2. Okay, so what if we then go first over to this one, and then this one, 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 and this one? That's time 3. And we're trying to find the minimum of that set. The problem is we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 locations to be serviced. by this agent or traveling salesperson. It is a it was named at a time of strong male hegemonic system dominance in computer science, and that's why it's called the salesman problem. We could probably just call it the salesperson problem, I think would be better. But if you're looking for this online or something, don't call it traveling salesperson problem, because it's still called the traveling salesman problem, as it was originally coined, the name at the time when it was first conceived. That being said, we'll just call it TSP to get rid of any gender bias there. We'll just call it the TSP problem from now on. So the TSP, we have 10 locations to be serviced, and trying to figure out the possible combinations of these 10 things is actually 10 factorial, like that. That's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. It's a big number. So to figure out which would be the optimal location, we'd have to test 10 factorial possible combinations of all the way to 10 factorial. Down here, we'd have time 1, time 2, time 3, all the way down to 10 factorial number of times. And that's just for 10 locations. This grows extremely fast. It grows faster than an exponential growth even. So 10 factorial, 11 factorial is a much bigger, 12 factorial much bigger. Once you get into 12, 10 factorial even, the numbers are just become too large to be tried that way. So you can't just try every possible combination to figure out what would be the optimal way to order the stops to minimize the time traveled. Because it could be any of those ways, possible ones. So that's called the traveling salesman, or TSP, I should say again, problem. And because there's too many to try manually like that, the traveling sales or TSP issue problem is what that poses. And it's a major focus of study in computer science. To find an algorithm that can solve the traveling salesperson problem for any arbitrary number of stops. In other words, computers, once you get into, let's say you have 100 stops, your computer, you need a supercomputer to figure out what the true best one would be. So the traveling sales person problem and has algorithms that utilize heuristics. That means learned, or I should say, pre-programmed behavior to try and find the best route. But there could be a better route in most cases, unless your N, your number of stops, is very, very small. And so the vehicle routing problem is a real issue. And ArcGIS, for example, can use the traveling salesman algorithm, but also with heuristics to try and get a better route. So various rules that are proprietary to the company that we can't reproduce necessarily to get the same routes that they would choose. But you'll get something towards the optimal route coming out of the analysis each time. Now you can imagine here, if you have a number of delivery drivers as well, then you have to figure out that for a number of delivery drivers. It becomes a very large, exponentially large, more than exponentially large. It's n factorial, it's a very large problem. So with the legalization of cannabis edibles, Alice Quapp and 3 friends, Bud, Ezra, and Blaze, are planning to open a medical marijuana production and delivery business in Orleans. They'll need to provide delivery within a 1-hour window, so there's a constraint on delivery, to bring the medication to elderly patients in a number of communal living facilities, which you see here in blue dots. So it's these communal living facilities that will require the delivery within a 1-hour window in the morning of the edibles. And they're going to be producing and shipping out of the Supperworks kitchen right here in Orleans. So they'll be using that kitchen in the morning to prepare and deliver the edible medicines. And that's a vehicle routing problem with constraints like this 1 hour window and how many drivers there are, how much each driver can take, what is the demand of each of these things as well. So there's demand issues in here. So it's somewhat like a location allocation problem too, because a certain number of things will have to be given to each or delivered to each of the locations. Now, for undertaking a vehicle routing problem, or VRP for short, the group has signed up 594 customers or patients at the senior residences, and they need to consume their edibles between 9 and 10 a.m. in the morning. So Bud Baker, he's going to do the baking, and Alice, Ezra, and Blaze, they're going to deliver the product in their cars. So our delivery fleet is 3 drivers. And they have to deliver all that within that 1 hour window. And we need to have then this table, which contains the information for the stops. So this is the stops in the vehicle routing problem. We need to have a time end, a time start, a service time, and a demand. So the demand is the number of doses that need to be delivered to each of the residences, and you can see them here. The service time is how long it takes to do that once you get there. So once the driver is there, how long does it take them to offload the doses? And that depends on a number of factors, right? But that has to be estimated. So in this case, the drivers have to actually go in. In some cases, they're required to deliver them to each of the residences' rooms. In other cases, they can give them to the front desk, and the front desk will deal with the distribution. So that's all figured out here in the service time right there. So for example, one of them has a 30-minute service time. So that driver can't do anything in terms of delivering anything else if they get that on their route, because they'll be there for 30 minutes and they'll only have 30 minutes left to do anything else. So that has to be all figured out. And the start time and end time. So that's the window time for each of the possible locations that are serviced between 9 and 10 a.m. for each one. And these are called orders in the terminology of the vehicle routing problem. So that's your orders table, basically. That contains the locations where deliveries will be made, as well as these fields, the demand, service time, time start, and time end. So this is showing in ArcMap, because you can't do it in ArcGIS Pro right now. Not in the version we have, so I'm not going to show anything in a newer version. Basically, load locations. It's done differently in ArcGIS Desktop. You right-click on the class orders, and you choose load locations. So that's slightly different than clicking on a button, which would say orders, and then the load locations dialog comes up, the geoprocessing tool. And here you specify, the senior residences is being loaded from. So we're loading from a feature class called senior residences. And then in here, within that little dialog, same dialog, the properties are set for the service time, time start, and time end. Max violation time is 0. The default value for that, and demand right here. That's the demand field that we just saw for delivery quantities. So that has to go in there. And there's other ones here that will also help control the analysis. We're not going to go into all the details of vehicle routing problems. This is just to give you an idea of how it works, so you're not afraid of it, and you have the terminology and the understanding to learn on your own if you need to do this type of thing. So we load the orders, and then we load the depot. The depot is where the deliveries start and where the delivery people come back to at the end of the day. They don't necessarily have to come back to it, but generally that's what a depot would be like. So we have the depots and we load locations. And in this case, it's just the kitchen, which is that Supperworks kitchen in Orleans. It's a single point. And the name is the kitchen name for that particular thing. And then the time, start and end. So this is the time that's in operation for this business, and that's from 6 to 11 a.m. So Bud will be there ready at 6 a.m. and will leave at 11 a.m. Then routes. So routes, we have to go to something called an add item, and that's where we add in each of the drivers. So for example, add item for routes, we then have a routes dialog come up. We give a name to that route, that'll be Alice. The description, car, and neither one of these are required, but it's good to have a name and know who's delivering what. The start depot name would be Supperworks. The service time at the depot, 0. So we don't consider loading time within that window. So the cars have to be loaded, obviously, before that 9 a.m. window. So if you were to consider loading time as well, you would put that in here as a positive value. The start time for the driver and end time. So Alice can only be there between 8:30 and 9, or can only work between 8:30 and 9. A delay at each stop. A 2-minute delay is put in here, meaning that there's a little bit of a buffer around that service time of 2 minutes. Not a lot. Usually probably something larger would be more appropriate, depending on the nature of the delivery. And then the capacity. How many things can Alice deliver? Can she fit in her car safely? And the total time that Alice can work that day, 60. And then you click OK, and that adds in one route. And then we do the same for the other two drivers. Ezra, again, 8:30 to 9 working. There's the capacity for Ezra, 250. And then finally, Blaze, 250 capacity as well. Other things pretty much the same. Description of the car, it's a hatchback. Ezra and Blaze have a hatchback, so they can have more than the compact delivery car of Alice. So we end up with 3 routes. Then we specify what's going to be minimized or in this traveling salesperson problem. And then that's done in the properties here. So there's a properties for the layer class, and we see that here, analysis settings. This is done in ArcGIS Pro differently. It's done on the network with the default meters or minutes, I should say, that we specified for the network attribute. So it's automatically used. So you specify here the time, minutes, meters, distance field units. In this case are kilometers. And then directions. So use minutes for directions. And that just means that when the directions are printed out for each driver, they'll be listed in minutes. So how many minutes from this point to this point to this point to this point, etc. Then you solve. And the solving there's not a run button, but it looks like a little grid with a line in it. And you click that in desktop, and it comes up with a message, in this case, that some orders could not be routed due to violated constraints. So in the first pass at this, we're missing the service out here to this residential home because we don't have enough constraints. And it will say, if we look at the properties of the one that it shows here, the Portobello Retirement Community Center, that's the unserviced one. And then the orders constraint here, we can see that it tells us down here that it cannot be delivered within the 1 hour time window. So even with the 3 drivers, that one's not serviced. So that means something has to change. For example, changing, let's say, the number of minutes somebody could work in a day, or their start or end time could solve that problem. So Ezra, Bud's paranoid about not making the deliveries on time. So Ezra says she can probably work delivering for an extra hour. And so we go back into that route for Ezra and we add 120 minutes instead of 60. And then we solve again, and then we have a complete solution right here for the deliveries. And so that means everything has been successfully routed now within that time window and everything. And so then you could print out directions for each driver so they know where to go, and then you're done. So for example, the button here shows directions, and this is directions for Alice. Alice's route is this one right there. So it says exactly, when to, where to start, where to go, and how long it should take. Now, of course, this doesn't take into account real traffic conditions. So real traffic conditions are taken into account, obviously, in this type of a model, because we don't have that information. But there are other parameters you can tweak and change to help take into account, what it might be like in the real world. And probably in this region, the real traffic conditions aren't heavy because it's in a suburb. So, you probably, they're pretty close probably to what they really would be in terms of delivery times and everything. And that's called a vehicle routing problem, where we have 3 vehicles, we have limited time and limited capacity, and they have to service N different stops.